In this video, we'll look a little bit more at unit conversions, specifically looking at mass versus force. So, the common units used in engineering, for engineering purposes, I recognize that you've seen a lot of others, especially with your chemistry classes. But for SI units, we usually use kilograms for mass and newtons for force. Okay? American engineering units, we get a little bit more creative. The two most common will be the slug and the pound mass for mass, and the pound or pound force, or the poundal for force. Now, in this course, we'll primarily use the pound mass and the pound force. So, how do we relate force and weight? Well, the equation is weight is mass times gravitational acceleration, and G, common accepted values on Earth, are 9.81 meters per second squared or 32.2 feet per second squared. You can use varying numbers of sig figs. I do recommend that you use a minimum of 3, however. Okay? Now, unfortunately, when you do that, you get nonsense units. And so what we have to do is we have to incorporate a conversion factor whenever we switch back and forth from mass to force. Okay? It's the equivalency between force and mass, and in SI units it's not so hard because we have one normal choice of force and one for mass, and so it's simple. 1 Newton is 1 kilogram times a meter per second squared. Okay? So the G sub C value that we get, normally we do mg over gc, and so gc is 1 kilogram meter per newton per second squared. Now, in English units or American engineering units, we usually are using pounds force and pounds mass, in which case G sub C is going to be the 32.2 or 32.174 pounds mass feet per pound force second squared. Now, there are some other less common ones, but the typical relationship is pounds force to slugs, poundals to pounds mass, and 1 pound force is 1 slug times a foot per second squared, and a poundal is a pound mass times a foot per second squared. Which sounds like that would be easier, right? But let's look at an example. Well, oh wait, first I forgot I had put this up here. A lot of times you'll have something where you know how to do the force in one or another units, in which case I don't discourage. Switch everything to the units you know, and then you can convert later. A variety of units that you might have run into in other courses. This is from Wikipedia, but they just show relationships between newtons and dynes, and kilograms force, also known as kips, pounds force, poundals. So all of these things here are variations on what we just talked about. Again, we'll mostly use newtons or pounds force for our force, and we'll mostly use kilograms or pounds mass for our mass. So this little example here, where we've built a catalytic reactor here on campus. Its job is to extract O2 from CO2. The total reactor weighs 41.3 pounds force. Okay? But this is something that might be very interesting. My son does aerospace engineering, so he's working on some Mars missions. It might be something that could be used to ship to Mars in preparation for a manned mission to Mars. So, if you're working on sending things off to Mars, you need to know the mass of the object. So, the mass for 41.3 pounds force, well, I just multiply by G, which is 32.2 foot per second squared, and divide by G sub C, which is 32.2 pound mass foot per pound force second squared, and I end up with 41.3 pounds force is 41.3 pounds mass. Now, I did this using the most common units. Obviously, you could switch to other things if that were more appropriate. But now you see why people tend to really confuse pounds mass and pounds force, because they appear to be interchangeable. Now, let's just take this the next step. We're going to send it to Mars. When it gets there, we want to know what the weight of it will be on Mars, because we need to know what anchoring force we'll need to use to make sure it doesn't move. Okay? Acceleration due to gravity on Mars is 37.5% of what it is on Earth, according to NASA. So, how are we going to deal with this? Well, mass doesn't change with location, weight does. So if we solve for the mass that's staying the same, that's the weight on Earth divided by the gravitational acceleration on Earth. Okay? So if I do this with the weight on Mars, the weight on Earth divided by the gravitational acceleration on Earth is then going to be multiplied by the gravitational acceleration on Mars. And the gravitational acceleration on Mars divided by that on Earth is 0.375. Okay? So the weight on Mars is 37.5% of our weight on Earth, so 15.5 pounds force. Now, typically we do all of our projects on Earth, so normally this isn't something that matters, but just simply so that you have an opportunity to see how this interrelationship between weight and mass could play out. Okay? So this ends this lesson. Again, if you need more examples on seeing how the mass-force interrelationship works, you might check out some other videos. YouTube has quite a few. Khan Academy also has several. Thank you.